Okay, well, thank you very much. So after spending the hour on Wednesday, sort of talking about various versions, and particularly reductions of the, I suppose, anti-self dual. So I should put an A in that second line there. Anti-self dual equations, and seeing how the geometry of curves and line bundles, so the things that sort of build important examples of integrable systems kept popping up in various ways, whether it was in the study of monopoles or various reductions of the self-dual Yang-Mills or the anti-self-dual equations from R4. Today, it's going to be the main story. This is where they they all occur in some sense. So what we've done now, we reduced by translations in 3 directions. We reduced by translations in 1 direction in R4. So now we do 2. And if you do this, you get an equation on a plane. But instead, I'm going to put, instead of a plane, I'm going to take a genus G compact Riemann surface. And so fix a degree and a rank n, and you repackage things. And you get 2 ingredients. You get a unitary connection. So let's see, whoops. This thing is not good at collaborating. So you get a unitary connection, and you get a got a section here. So a section of the endomorphisms of a bundle tends to the 1 forms, holomorphic 1 forms. And your equations, your self-duality equations, become first that this section phi, the Higgs field, is holomorphic. So the d bar part of the connection gives 0 when you apply it to phi. And there's a second equation, which is just that the curvature of the connection is minus the commutator of phi with its Hermitian conjugate. So A is a Hermitian connection, so you get you also get that the 1, 0 part of it applied to phi star will 0. You just take complex conjugates. And this sort of 2 out of 3 principle basically applies here. Now, to make this more manifest, you can repackage things and put in a parameter here. And the statement is that these 2 operators, lambda dA plus phi and d bar a plus lambda phi star, commute for all lambda. And so you basically have a whole complex plane for the moment, but essentially in the end a whole sphere of complex structures implicitly in these equations. And the one we're going to concentrate on is the lambda equals 0 equation, and that's just the d bar phi equals 0. I should say that if you take the lambda equals 1, you're getting the flat GLNC connections, and there's a whole story there in terms of character varieties of Riemann surfaces. But we're just interested in, for the moment, in this E phi business. So our moduli space that we're interested in is a space of pairs, E, be a rank n holomorphic bundle, and phi, which will be a section of these endomorphisms tensor the canonical bundle. Okay. And there's a slope condition, a semi-stability stability that you want for the moduli space, and that's you want for any invariant subbundle, and the invariance is important, that the ratio of the degree over the rank is less for stability or less or equal for semi-stability than that of E. And an important feature of this is the condition for stability of just the bundle is you drop the phi invariance. So in other words, if your bundle is stable, then any phi will do. And unfortunately, or fortunately, a lot of the interest is the cases when the E is not stable, but there's a phi to stabilize it. Okay, so these are the moduli spaces. And symplectically, sort of you're inheriting from the hyperkähler sort of picture, which is sort of manifest in R4. You're inheriting a holomorphic symplectic structure. There are various ways of describing this, but a simpler way, I mean, the sort of goofiest way, is to notice that if you just take the moduli stable bundles, then a large, well, basically dense, piece of the moduli of Higgs bundles is just the cotangent bundle of N. And the reason's quite simple, that if you deform a bundle, what do? Well, it ends up being an element of this group. The reason is that you write a deformation, sort of put in a little parameter epsilon, and write it in the obvious way where you're taking a transition function and so that's the transition function of 0, and you put in a small parameter, and this thing here ends up defining a class in there. And so it's naturally the element of H1 of the endomorphisms. And then dually to this, with Serre duality, is the space of H0 of ND tensor KX, which is the Higgs fields. And so what you're getting basically is something that looks a lot like a cotangent bundle, but has some extra stuff stuck in around the edges that makes it not quite compact, but a little bit more compact. So some directions get closed off. Alternately, there's a sort of deformation theory definition. So you take a pair of E and phi and you deform it, and sort of hypercohomology calculations, and you get basically the tangent bundle of M maps to the deformations of bundles with kernel the deformations of the phis. And then when you dualize, things sort of switch around, and but you get the same thing for the cotangent space. And so if you just take the identity map here between the two, you'll get the symplectic form. So it has a symplectic structure, and then there's this wonderful. So alternately, you could do it starting in a space of infinite dimensional spaces where you're just dealing with a sum of two spaces. One is the d-bar operators, and the other is of the smooth Higgs fields. And you've got it. Your moduli space is formally a reduction by the action of the gauge group. Okay, so now you've got an integrable system, and this is the main actor here in some sense. And the coefficients or the functions that build up this set of commuting Hamiltonians are basically the eigenvalues of phi. Now, of course, it's not an endomorphism; it's a form-valued endomorphism, and so get something a little bit different. If you take the powers of phi, you'll get and take a trace. You'll get these sort of well, I forms, if you want, or powers, ith power of the canonical bundle sections. And this is a fixed vector space. Your x is fixed, so you can just take a basis and decompose. And you'll get components that should be your Hamiltonians. And the theorem is that of Hitchin is these Hamiltonians Poisson commute, and they give you a completely integrable system. Now, how would you like to sort of think of this geometrically? Well, the simplest way is to combine these Hamiltonians into one object. And you take a spectral curve. So normally, if you're taking the spectral curve of a matrix, you just get a spectrum of a matrix. You get n by n. You get n points in the line. Well, here it's over a base, so that's fine. You would think of the trivial bundle, but of course, these are form valued, and so where your spectral curve is living is in the total space of the line bundle. So this, and this is sort of comes back later on, is naturally a symplectic surface. So it has a tautological two form on it, basically. And well, of course, basically it's the cotangent bundle of X. So as I said, it has a tautological section of the lift of the canonical bundle to itself. And so the spectral curve combines all the Hamiltonian flows. And then you can do the following, which is just take the co-kernel of phi. So you get a map, in other words, from E, put in a twist, because you have to, and map from essentially from the lift of E to itself. And where is this not an isomorphism? Well, it's where you're at the spectral curve, where you're at an eigenvalue. And so you get a sheaf here that's supported over the spectral curve. And basically the nice thing about this is that your moduli space gets parametrized in the following way. You've got, normally it was a space of E and phi, and it becomes a set of spectral curves and line bundles over it. So you've turned your vector bundle to a line bundle. So generically a line bundle, of course, because you could have multiplicities and things like that. But if sigma is smooth, multiplicity 1, then you're getting a line bundle. And sort of coming back this way, well, what do? The vector bundle E will just be the direct image. You've got a curve, spectral curve living above X. So you take its direct image to X, and you get back E. And phi is just the effect of multiplying by the fiber coordinate, if you think about it. Another nice feature is if these curves are irreducible, the spectral curve is irreducible, then the stability comes for free. The point being that if you want a destabilizing object, you will need some phi invariant subbundle, and so you'll need a subspectral curve. And if there's no subspectral curve, then there's nothing to destabilize. Okay, so the sort of general picture is this Hitchin fibration, where you've got the sort of linear space of just the Hamiltonians. And you've got a family. So each point here basically determines a spectral curve. And then you've got the set of line bundles over sigma, which are, there are abelian varieties. So you're getting the picture of a completely integrable system, which is a family of tori, this time complex tori, living above sigma. And the nice thing is Hitchin shows these fibers are actually compact. In most of the concrete examples of integrable systems, though you do get tori, you can even complexify a lot of them, there's usually a divisor somewhere on the abelian variety where things go wrong, but here it doesn't. And so this is particularly nice. Another nice feature is the symplectic form that you had abelianizes. So you have basically two sort of rival fibrations that are sort of living on this picture here. One is the set of bundles, and so you've got the space of E phi projecting to E. And another is the set of spectral curves, so the set of sigmas. And you've got these Jacobians here projecting down this way, and they're generically transverse. And yet the symplectic form basically can be made to sort of decompose transversely. And the way you can think of it is that, well, say you've got a spectral, oops, oh damn, it's, oh, there we go. You've got spectral curves here, you've got a line bundle on it, and you think of the line bundle as being determined by a divisor, just extend the divisor a little bit to a neighborhood. And it gives you a way of, if you want, when you're deforming the curve, of keeping the line bundle fixed. And conversely, you can keep the curve fixed and move the line bundle. That one's for free. And so you can think of the tangent space as being decomposed this way. And you notice these are Serre dual. And so this is a very nice feature, because of course on the sum of a space and its dual, you can write a natural symplectic form, symplectic pairing. And indeed, it is a symplectic structure. The differential of the, and then you can integrate these systems in a fairly concrete way. The differential of the Hamiltonian. Well, if you think about it, what is the differential of a Hamiltonian? You're taking the derivative of the coefficients of the spectral curve. And so it'll give, for a given variation of the spectral curve, it'll give you apply this thing, it'll give a number. So the section, it gives you in the end a section of the conormal bundle. Now, since the canonical bundle of the surface is trivial, the conormal bundle becomes the I'm getting confused now. It'd be dual to a one form on the spectral curve. Okay, so now you're in this space, or in its dual rather. And by the symplectic pairing, it'll get identified with a cocycle, an element of the first, the H1 of the, and this can just be given by a cocycle, and then you'll get an explicit flow, basically, of line bundles, integrating your Hamiltonians just by tensoring the line bundle with this multiplying the transition functions by these cocycles, they're exponentials. Another important feature is that this can be allowed. You can allow some poles, and so I'm going to just take a positive divisor on X. And now I'm going to allow X to be of arbitrary genus. Before I had genus 2 and more, and this time you can take it arbitrary. And this is rather nice because what essentially, I think, basically 3 simultaneous theses show that this is a Poisson manifold. Again, you'll get a spectral curve. So you're not getting a symplectic manifold, you're getting a Poisson manifold. And you get a spectral curve. Here's X. Here's sigma. Above the divisor on X, so these are points. You'll get a fiber here. And basically, the symplectic leaves are obtained by fixing the phi, at least the adjoint orbit of phi over d. So in generic terms, basically your symplectic leaves are obtained by nailing the spectral curve down over the inverse image of d. Okay, but you can do the same story. You can take you'll get a sheaf L. As I was noting, the Casimirs, the functions that Poisson commute with everything, are just given by the intersections of the spectral curves with D, or it's rather its inverse image. And again, you have this picture of pairs of E of phi become, again, this picture of spectral curve plus line bundle. So it's all very nice. The special case that lies and ties in with basically not every integrable system, but a huge number of things that have been studied by a whole bunch of people, is when you take x equals to p1. And mostly just take e to be of degree 0. So there's a generic locus for these, which is just the cases when E is a trivial bundle. And so now your Higgs field becomes basically a function. So a matrix valued function. So you fix a divisor, D, and for simplicity, I'll just take them to be distinct. And so you can write out, at least for this trivial E set, you can write these Higgs fields out very explicitly. And sorry, excuse me, delivery at my door. So we'll deal with that later. So as I was saying, you can write these out explicitly, basically as just meromorphic matrix valued functions. The vanishing at infinity is basically the canonical bundle being O minus 2. And of course, this is up to conjugation because these are trivially, they're not trivialized. And so you've got some freedom for quotienting by here. But the symplectic leaves, as I said, we're fixing the coadjoint orbits. And basically, you've got this link to some classical symplectic geometry, which is that the symplectic leaves are products of coadjoint orbits of the elements AIs by this, and it'll be a symplectic quotient. So here you're setting the moment map to 0, and then you're quotienting by the action of GLNC. There's another way of looking at this, which is that you think of the polynomial loop algebra for GLN. So those are sort of series with positive, or polynomials anyway, positive coefficients. You take its dual under taking the residue at infinity in the trace. So it'll be the negative Laurent series, again, expanded around infinity. And the finite dimensional coadjoint orbits, at least if your group is, your algebra is semi-simple, will just be these things with simple poles, or multiple poles possibly, but just given by these sort of expressions. And then there's a sort of theorem that dates from the 70s, the Adler-Kosten science theory, that tells you that if you take these Hitchin Hamiltonians, the flow corresponds to these Lax equations. And since the bracket is an infinitesimal conjugation, you can see that the spectrum of A of lambda is being preserved. And there's a meta theorem, which is anything you're interested in somehow fits into this this picture or its variants for other Lie algebras. And also these much studied finite gap solutions for the various integrable PDE. So I don't know, KDV, nonlinear Schrodinger. There's a couple nonlinear Schrodinger. There's a whole bunch of them also fit into this. For a PDE, you're looking at the commutativity of two flows. So you've got two Hamiltonian flows. They're supposed to commute, and that commutativity gets translated into a solution to the PDE. This is false, except that, people were saying, for example, that the Kovalevsky top didn't fit into this. Then somebody came up with a solution. Then people were saying that other examples, the Calogero-Moser systems come up. Curiously, actually, the Calogero-Moser system is one case where probably it doesn't really fit in any nice and decent way, because really, instead of the corresponding to a Riemann surface, it really is living on an abelian variety built from an elliptic surface and a root lattice. But even then, the standard sort of GLN Calogero-Moser or SLN Calogero-Moser can be made to fit into this context. So they're very useful. I should say there are also exceptions because and I'll be coming to these because there's some generalizations. Okay, so you've got a whole bunch of equations that sort of fit into this framework, and you can generalize to arbitrary Riemann surfaces. And well, I was going to give you an example. So this one dates from 1859. And it's the motion of a particle on the n-1 dimensional sphere under the influence of quadratic potential. You realize it is a constrained flow on R2n, so they're details, which I'm skipping. But basically, you write a 2x2 matrix from the coordinates that looks like this. Here's your parameter lambda. You've got a Hamiltonian, which modulo sines and factors of 2 should look something like this. It will have a Lax equation for its flows, where the B is given like this, and you can integrate. And so, okay, Neumann integrated it, and the question basically is how does it fit into this? And so we already had the symplectic structure for our Hitchin systems, in some sense, abelianized, so it lifted to the spectral curves and the line bundles. And the question is, how do you do this? And there's a very nice geometric way that ties in with the totally classical 19th century way of doing these things, which is as follows. I've got a space of pairs, spectral curve and line bundle. I'm going to be thinking of this line bundle. So here's my spectral curve. And I'm going to be thinking of this line bundle as given by a divisor. Now, that, of course, isn't unique. And so what I'm going to do is build some uniform twist in. So I'm going to take just a little curve here, a segment of curve, intersecting the spectral curves with an appropriate multiplicity, and sort of taking the twist of L by this divisor, so that the resulting, which I'm again calling L, has generically a single section. So this happens when the degree is the genus. Okay, then basically L will correspond in a unique way to a divisor. And this divisor has G points in it. And you do the following interesting thing. You've got your spectral curve and your divisor, and you do this. So what are you left with? You're left with G points. Oops. G points in this surface, Kx. And that's the theorem. We were very proud. Malcolm Adams, John Harnett, and I were very proud in this theorem, and developed into various extensions and things like this over the years, and went on like this. And we thought we found something nice. But John Harnett sent me an email once saying, look up a paper of Garnier in the Rendiconti del Circolo Matematico di Palermo in 1919. And sure enough, for a fairly general case of these things over P1, these points are Darboux coordinates. Now, in what sense they're Darboux coordinates? Well, you have the symplectic form. So you could choose Darboux coordinates on a neighborhood of each point. And then basically your system is the symmetric product of the surface. Well, we don't say symmetric product, we say Hilbert scheme, because this is smooth. So, it smooths it. The symplectic form extends naturally. And so it's the natural locus, basically, is the Hilbert scheme. But it's the result is kind of in there. In of course, it's do the following substitutions, insert into the integrals, and then, divide by 3, and it happens. But it was there. So with this, you can do a 19th century integration of your system. So you can you take a coordinate, let's call it lambda again. So here's x. You're taking the associated coordinate cotangent coordinates zeta, and so your symplectic form is d zeta, which d lambda. You have these Hitchin Hamiltonians, there are g of them, and you can then say, well, once I fix the Hamiltonian, it fixes the spectral curve. And so I'm on something that's one-dimensional, so that zeta becomes a function of the lambda, because it's one-dimensional. So there's some algebraic thing that gives you the result. And you then define a generating function. So it's the integral of this expression, base d lambda, and you sum you do this for each g. Now you notice that here are your Hamiltonians, and here is 1/2 of the Darboux coordinates. So in other words, the Lagrangian sort of subset. And well, it's fairly obvious that if you take the derivative with respect to lambda mu this, so you're keeping the pi's fixed, then the derivative of the integral is just the integrand, and you're getting zeta mu. And then it's a standard trick, basically using d squared of g equals 0, that these quantities linearize the flow. And then the nice thing, that's basically the Poincaré residue formula, is that when you take the partials with respect to the pi's, you're getting a basis of abelian integrals. And so you've integrated your system by quadratures in an entirely sort of classical way. You can write down, for a given curve, you can write down the abelian integrals. They're basically this formula tells you what they are. And of course, the flow of abelian integrals, if it's flowing linearly, the corresponding line bundle is flowing linearly, because the abelian integrals give you the integer the linear coordinates on the Jacobian. So that's the story. And if you go back to the Neumann example, you get these classical coordinates, because these things are computable. So the lambda mu's were these ellipsoidal coordinates. So you take one of the coordinates, one of the coefficients of the matrix, and it's where these things vanish, basically, that you're getting these things. And there's a sort of dual expression for the zeta mu. And so you're getting your your coordinates in which these things flow. You will then write out your expression with respect to the sort of standard coefficients for the Hamiltonians, and you will find the things that linearize the flow and their hyperelliptic integrals. So a very, very classical story indeed, and it basically reproduces what Neumann did. These systems have variants. There's a cousin, which is the Slyannon system. This seems to only work for genus 0, so the genus of x, right, sorry, equals 0 or 1. There's the sort of earliest version basically uses the rigidity of bundles in low genus. So this means genus 0 in general, or in some cases elliptic curves if you fix the determinant. There's a more general version that comes out of work of Ettinghoff that can use the fact that bundles basically on an elliptic curve all reduce to tori in some suitable sense, or on a nice big open set, and use that version too. But for a moment here we've got this story. So your bundles basically for genus 1 only they don't deform, so they're rigid if you're taking the stable bundle, and so you could, if you're covering your base curve x by two open sets, say a disk and then the rest of the curve, you can do a splitting of essentially the loop algebra of SLE into a bit on the U plus and a bit on U minus, so direct sum. And so you get projections and this R matrix, which is a difference of projections. And on the loop group, you're finding there there's a left and right derivative. So you can either take left translation to the origin or right translation. So you can do this or you can do that. And the bracket, the Slyannon bracket, is basically this expression of two functions. So it gives you a Poisson bracket. Gives you a bracket on the space of the set of automorphisms of E. So somehow you don't want to think of them as endomorphisms, you want to think of them as automorphisms. Of course, they're all matrices. But there's a reason. And so you'll still have spectral curves, you'll still have the sheaf L, but now you see your symplectic leaves are a little bit different. So here's sigma, or here's x rather, and you've got a sort of P1 over it, in which the spectral curves are living. And here's infinity, here's 0. And you see, whereas before for the Hitchin systems, the thing that determined the symplectic leaves was the intersection with the inverse image of a divisor. So that doesn't happen here. And instead, it's the intersection of a spectral curve with either 0 or infinity. In other words, where your meromorphic automorphism either develops a pole or ceases to be an automorphism and is just an endomorphism. So I'm sorry, that should be a is 0 here. Right, so it's a slightly different different system, but again, this one it's well known. It has applications and comes up in various contexts. But indeed, you still have this feature of a symplectic surface, and now this time you notice that one of the coordinates, the sort of vertical coordinate, is it's the logarithmic differential that comes in, and that reflects the poles at 0 and infinity. So again, you're getting a Hilbert scheme of a surface. Okay, well then you're starting to see there's a bit of a pattern here. You're getting Poisson surfaces. And there's a theorem of Bartocci and Macri. It gives you at least complex Poisson surfaces, and there are rather few of them. There are, of course, the symplectic surfaces that you'd expect, abelian surfaces, so tori, fine. K3 surfaces. But there are also ruled surfaces, which are the examples we've seen. And it turns out that the ruled surfaces are actually quite restrictive. You see, in general, you'd imagine you take the projectivization of a vector bundle and all would be well. And it doesn't work this way. So you're getting well, you're getting either a sum of two line bundles, and one of which is the canonical bundle. I mean, once you've normalized, because you can tensor the two by something, it doesn't matter. So it would be O plus the canonical bundle twisted by a positive divisor. The Poisson tensor is fixed. Okay, I'm all mixed up in my. So the picture here is you've got a rational, a ruled surface, and your Poisson structure basically has twice infinity, and possibly this divisor D or something equivalent to it. So that's G arbitrary. For G1 or 0, you've also got ruled surfaces of the form trivial bundle plus a line. And here you've got this possibility of a, oops. Ruled surface, but now the singularity, the 0 of the Poisson structure is at 0 and infinity. And then there's, for G equals 0, there's some extra thing. And then there's this sort of fourth rogue case, which is that you can build the non-trivial extension like this, which will be essentially the one-jet sequence of a line bundle. So the one jet of a line and tensored with its dual. And so, which system corresponds to a Hilbert scheme? Well, I mean, you can take the Hilbert scheme of these things, you can put curves in them and develop the thing, but it doesn't seem to correspond to something else in a sort of sensible way. But then maybe that's just my lack of imagination. These correspond to the Hitchin system, and these correspond to the Slyannon. And so the final question was, or the question we were discussing this with Indranil Biswas, and so what does this correspond to? And it turns out there's a nice moduli space where deform the Hitchin system. So you take a bundle, space of bundles, and you look at, this is a rank 2 bundle, so that doesn't look too good. But this maps to endomorphisms of E with a kernel. And you take maps that map to the identity here. So you're getting a sheaf of things. It's affine, it's not linear. But it's a torsor over the forms. And so you can define a spectrum for these, and you can define a spectral curve, and it's living in P of V. And you'll get a line bundle, integrable system, and the whole business, and the divisor coordinates and everything works. So this is the system. I don't think I've ever seen it elsewhere, but it's there. A final remark maybe is that the Hamiltonian systems, I mean, people have been working, a lot of people work on these things. And there's a trick for integrating a Hamiltonian system in that if you dig up, you somehow produce a family, a compatible family of Poisson structures. And so what compatibility means is that you've got one Poisson structure and you've got another Poisson structure, and you have to be able to take linear combinations of them and still get a Poisson structure. And as the Poisson structures in higher dimensions all satisfy a differential equation, it's the analog of being closed for a symplectic form. Well, a symplectic form in 2 dimensions is automatically closed because there's no place to take its exterior derivative to. And for the same reason, basically, the Poisson structures in 2 dimensions, anything of the right, they're all Poisson structures, basically. So there's no equation to satisfy. So if your system is secretly the symmetric product of a surface, and you take 2 of these surface symplectic structures and take a combination, those symmetric products are also, the Poisson structures are going to be compatible. And so basically it explains in a few lines a whole industry showing that these various Hamiltonian systems with their like spares and such have multi-Hamiltonian structures. It's basically the fact that secretly they're all symmetric products of surfaces. And so this is a sort of nice and useful remark. Looks like I've ending there, so maybe I'll just let you, all those courageous people in India who are falling asleep, finally collapse. So thank you for your patience.
Thank you, Jacques. Do we have any questions? We had one question in the chat, but I think that we sorted that out. It was asking, in your description of the meromorphic Hitchin system of Q1, why were you quotienting by the general linear group? You can.
Oh, it's just the automorphisms of the
just the automorphisms, yeah.
So that's the thing. I mean, it is intriguing that in those systems, the compactification is just taking all the bundles that aren't trivial, and they're somehow giving you the closures, which is kind of nice.
Oh, we have a new question. It's asking, do we require Poisson structures for Hamiltonian systems? I actually don't understand the question, but
I mean, I suppose it's sort of, at least implicitly. I mean, you need, it's the mechanism that turns the function into a vector field, which is sort of what you want. So I guess, yeah.
thank you. Do we have any other questions?
So have people looked at the analogous thing for Dirac structures by any chance? Classification?
Oof. I don't know. You'd have to ask them what looks at these things. I'm afraid I haven't. It's an interesting question. I mean, I don't know.
Sorry, I didn't get the question. Pranav, can you repeat it? What was the question?
So he talked about the classification of Poisson structures interventionally. I mean, of Poisson things. So I was asking if there's an analogous thing for Dirac structures. People have looked at.
Yeah, I don't think anybody has done that, but that's going to be a much more complicated question because you need algebroids, and the moduli of algebroids is not going to be so simple, right?
Mm-hmm.
I mean, one thing that helps here is it's linked to the positivity of the surface, right? So it's you know, you're dealing with the low end of the Kodaira classification. But yeah,
right.
So I don't know.
Yeah, I had a similar, but going in a different direction question. So this interpretation, Hilbert scheme interpretation of integrable systems. Has anybody studied how it interacts with quantization? You could.
Well, yes and no. I mean, it's an interesting question, and it was one of Harnad's obsessions for a while, is because it seems to, I mean, there's a sort of enigmatic statement that it was somehow linked to geometric Langlands. Now, Harnad and Winternitz did a quantization of the, I forget which classical system, but using these Darboux coordinates and writing out, and all operators very explicitly, the Hamiltonians and an energy like Hamiltonian, quadratic, and the momenta and so on. And the thing was, it led to there was a quantum separation of variables, not just the classical.
Mm.
So the question seems to be of interest. The hard thing, and there's been a few papers, Rutzoff had a few and things like, but getting that to work, on an operator level with any explicitness, I suppose, is not.
Yeah. Okay, then maybe we can break for now, and we'll have a watch party for the people basically in the Western Hemisphere in an hour and a half. And thank you, Jacques, again.